Okay, I want to talk about Huffman code and the Huffman tree. Huffman code is an optimal prefix code with the shortest expected length for a given distribution, which can be constructed by the Huffman algorithm. I'm going to talk about the Huffman algorithm in a few slides back, okay? A few slides in the future. Uh, so again, the objective is to minimize the expected length given the distribution, and we can compare this description length, expected value of description length with the entropy. Since the distribution is given, entropy can be calculated. So here, I want to describe the algorithm using an example, and then I will give you the formal description of the algorithm. So here I have 6 items, and each occurs with a probability given this way. And I uh, uh, have listed the probabilities in the descending order, like this, 0.4, 0.2, and so on. And the algorithm says that on the list, I find the least probable items, 2 of them. In this case, D is equal to 2. So I find 2 items that are least probable and group them. So in this particular example, D is equal to 2. And I group these 2 first in this particular example. And then after you have grouped them, you write the addition of the 2 probabilities. So it becomes 0.2. And once I have done this, then I have reduced the risk to be 5. So I have 0.4, 0.2, 0.1, 0.1, and 0.2. So these 5 items, I again find the 2 least probable items. Since D is equal to 2, then these are the 2 items. So 0.1, 0.2. So I add the 2 items and write down the probabilities right here. So it becomes 0.2. Then the list has gone down by 1. So the list becomes 0.4, 0.2, 0.2, 0.2. And I need to select 2 least probable items again. In this particular case, I have chosen these 2. I could have chosen these 2, but I didn't in this particular example. Okay, so that is what is happening. So Huffman code is not unique. So you could have come up with different Huffman code. But each Huffman code has the same average description length. We can prove that, and we can, for proof, we can resort to the textbook. Probably what we do here is that we will have a couple of examples that lead to the same minimum description length. So the first particular case is given by this example where I have chosen to combine these 2. So after I have combined these 2, then list has gone down by 1 again. So the probability list is 0.4, 0.2, and 0.4. And then I also need to find the two least probable items. In this particular case, I have chosen these 2. I could have chosen these 2 as well, but I didn't. if you have done this, then you will have a different prefix code, but with the same expected length. So Huffman code is not unique given the distribution. You could have come up with different prefix code, but each prefix code that you came up with has the same minimum description length, have the same description length. Okay, so I have chosen in this particular case to combine these two, and then it becomes 0.6, and the last item is uniquely determined because there are only these two items, and then I combine the two, and I finally constructed the Huffman tree. And after I have done the construction of Huffman tree, then I assign ones and zeros for ups and downs. So in this particular case, I have going up to be 1, going down to be 0. I could have reversed it. Then I could have come up with another Huffman code. Okay, so in this particular case, going up is 1, down is 0. So using this convention, let's find the prefix code for item I equal to 1. So first one can be described by going up and up again. So it is going up and up. So it is 1, 1. And the second item right here can be described by going up and down right here. So going up and down, so ones and zeros. And the third item is down, up, up. So it is 0, 1, 1. Fourth item is down, up, and down. So it is 0, 1, 0. Fifth item is down, down, up. So it is 0, 0, 1. Sixth item is down, 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 which is this. Okay, so this is the Huffman code constructed by this convention using this tree diagram. And again, we note that this tree diagram is not unique. So you could have different tree, and then you could have come up with different prefix code. But the expected length of each prefix code is the same. And I have a typo right here. In this particular prefix code case, the length of each code word can be described, and Li here is equal to 2 because the code word is 1, 1, and Li for the second item is 2, and third item is 3, third item is again 3, 3, and 3. So the length for each code word is 2, 2, 3, 3, 3, 3. So that is the correct item. So once I have done this, calculated, then I can calculate the expected length. So what is the expected length? That is given in next chart right here. So there are 4 items with the there are 2 items. So first one is length 2, so 2 times 0.4. Second item occurs with 0.2, and the length is 2. And rest of the 4 items each occurs with 0.1, and the description length is 3. So if I add them all up, it is equal to 2.4. And I have this distribution given, so I can calculate the entropy, which came out to be 2.319. And now we can note that the expected length is greater than the entropy. So that's one example. I could come up with different example. I could come up with a different Huffman code. Okay, so let's try to do different Huffman code construction. And here, let me do it one more time. I is equal to 1, 2, 3, 4, 5, 6, and the probabilities point is equal to 0.4, 0.2, rest of them all 0.1 was. And let's start the Huffman algorithm. The algorithm says find the two least probable items. Here again, the example is binary description of code word. So D is equal to 2, and I will choose these two and add the two probabilities. Then the list has gone down by 1, and then I have 5 numbers now, 0.4, 0.2, 0.1, 0.1, 0.2. And out of these 5 numbers, I need to find the two least probable items. And in this case, these are the two. So that is uniquely determined. And I add the 2, which is 0.2. And the list has gone down by 1, so the list size is 4. So 0.4, 0.2, 0.2, 0.2. That's the list. And in this case, I have chosen, I want to choose to add these two. Okay, so I add them up, and then I bring it out, and then I have now list of 3, and which one do I want to combine? In this particular case, I have chosen to combine these two. Then this becomes 0.6 and 0.4 right here, and then I add the 2. I have finally constructed a Huffman tree. And let's do code word assignment. So going up is 1, going down is 0. So the first item is obtained by going up by once. And second item is down, up, and up. So down, up, and up. So that's the second item. The third item is down, up, down, up, down, up, down, up. The fourth item is down, up, down, down. Oh, sorry. Down, up, down, down. Okay. Okay. Down, up, down, down is the fourth item. How about the fifth item? That is obtained by down, down, up, down, down, up. The sixth item is down, 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 down. Okay, so these are the collection of code words, and then for each code word, I can calculate the length of a code word. So here is length is 1, 3, 4, 4, 3, 3. So that's the length, and I can calculate the expected length, which is length 1, 5.4, length 3, 5.2, length 4, 5.1, another one, 5.1, and the length 3, 5.1, two of them. Okay, so what do I have? So that is 0.4, 0.6, again, plus 0.3. So this is 1.0 plus 0.8 plus 0.6. So if I add them up, that is 2.4. So that is 2.4 bit. So this 2.4 bit is the same as the 2.4 bit required for previous Huffman code. So there are two different Huffman codes for a given distribution, but what we have verified is that the two code has the same expected length. And indeed, by following the Huffman code construction algorithm, one can come up with different code, but with the same expected length. Okay, so those are the two items of Huffman code example. There are another one. We can record the 8-horse race problem, and the probability distribution was given like this, and we note that this distribution is nothing but dyadic distribution. Since it is dyadic distribution, the expected length is equal to the entropy. And as we see this tree that can be obtained by following the Huffman algorithm. So for example, these two are the least probability. So we add the 2, and then we add the 2, and then we add the 2 together. So that's for this item. After you have done that, that is 1/16, and then we add the 2 1/16 nodes, and which becomes 1/8, and then we add the 2 1/8s, and then we add the 2 1/4s, and then we add the 2 1/2s. 2 halves, 2 halves, and we finally have this tree structure. So once I have done that, then I assign 0 for upward, and then 1 for downward. Then I have this code word description. Once I have done this, once I have obtained this, the length is 1, 2, 3, 4, 6, 6, 6, 6, and these length is actually okay. Let me write it. This length follows. Oh, sorry. So this length follows what this yeah. So it is exactly following this. So for example, of this half, the log of 2 of inverse is basically 1. So that is length 1. Okay, and the same with this one, 2 to the power of 2, so which is length is 2, this one 3, this one 4, this one is 2 to the power of 6, so it is 6. So this description length exactly follows this relation, and without taking the ceiling operation, this left right hand side is exactly equal to integer. So in such a case, we have this result. That is, the expected length is exactly the same as the entropy. Okay, so here is the Huffman encoding algorithm. We want to construct a tree in the following routine. First, have the probabilities and the index listed in the decreasing order. Second, go over the list and locate two indices with the lowest probabilities. Group these two low probable items and add the probabilities and label it for the group. Now note that the size of the list is reduced by 1. This is the case for binary case, and repeat the second step exhaustively. So once a tree is completed, then we can assign 1 for up, 0 for down. Okay, and then we can construct Huffman code using the procedure. Okay, and this one is optimality of Huffman code. Basically, given a distribution, there could be many Huffman codes, as we have seen in examples, which all lead to the same expected length, and we can call the Huffman tree procedure Huffman coding. So basically, the procedure that I have shown you with the examples is Huffman coding. And the Huffman coding is optimal in the sense that when you calculate the expected length, that is the minimum. And we can see chapter 5 for proof, which is done by induction.